Hello and welcome to the Daily Space for today, Monday, February 18th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. One of the things we talk about a lot around here is planet formation, or more importantly, how we really don't understand planet formation. Part of the problem is we only had one example of solar systems for nearly 400 years between when Galileo started making scientific observations and when 51 Peg was discovered in 1995. 400 years is a lot of years for theorists to theorize about how to create solar systems just like our own. But the thing is, most solar systems aren't just like our own. In the years since, people have flailed about trying to explain the great diversity of solar systems we're now finding. And along the way, lots of contradictory ideas have been put forward. Part of the problem is we don't have a lot of data to describe the in-between steps in solar system formation. We see the big picture of star-forming regions becoming star clusters. We see the propylid step, where baby solar systems are cocooned in gas and dust. With radio telescopes, we've started to see disks with what we think are forming planets. And with missions like Kepler, we see fully formed systems in every possible configuration. What we haven't had are observations of the intermediate step between propylid and planetary disk. At least we haven't until now. A team of observers using the Very Large Array and the Atacama Large Millimeter Array have now observed more than 300 baby planet-forming disks that are just starting to spin up. All these systems are part of the Great Orion star-forming region. Now, as astronomers, we often say things like, all stars in a star cluster form at the same time. I've said that a bunch. But the truth is, they may gradually come into existence over a million or millions of years, which, from the perspective of star formation and cosmic time, is all forming at the same time. But from the perspective of planet formation, which is super fast, a difference of a million years can be the difference between no planets existing in a system and all the planets being fully formed in a system. Only by looking at a whole lot of different solar systems could this team have any possibility of catching any systems in the act of just starting to form worlds. Out of the observations of more than 300 systems, they were actually able to identify 4 protostars that had just started to turn on, systems estimated to be less than 10,000 years old. These systems have just started to have jets slowly flowing from their poles. The stars appear irregular and blobby in radiolite. According to the team researcher Nicole Carnath, we think that they are in one of the earliest stages of star formation. By studying these stars, we can begin to build a detailed film of what star systems look like during a new stage in their development, a new early stage in their development. While it may seem like a waste to observe more than 300 systems to find just 4 that match, special early on requirements, we want to assure you that no piece of data in this survey will go unused. This work has already produced 2 new papers appearing in the Astrophysical Journal and has detailed how the size of protoplanetary disks evolves as the forming star in each system grows by stealing material away from the disk. It's literally star-eat planet-forming material out there. And this interplay between forming stars and their planetary disks can have profound effects on how planets form. We observe young stars blasting light all through their inner solar system, driving material out. In fact, so much light is out there, it can push material outwards and completely dry up an inner solar system. Just how far things get dried out is still being sorted, but we do see where all the water went, and that place is the outer solar system. What we observe is a difference of composition, with the sun having far fewer atoms capable of combining to form water than what we see of actual water in the atmosphere of worlds like Jupiter. In new data coming to us from the Juno mission, observations of Jupiter's equatorial region show the atmosphere of Jupiter is roughly 0.25% water, which doesn't sound like a lot, but is actually 3 times what we see in the composition of the sun. This data comes from looking at Jupiter in microwave-colored light, which is readily absorbed by water. Using Juno's microwave radiometer, scientists could study how Jupiter's water content varies with depth, and this is how they got their water-rich results. Now, these results don't necessarily reflect the composition of the entire world, and future orbits will allow these same kinds of observations to be made of Jupiter's polar regions, which have very different temperatures and structures than what we're seeing in the equatorial regions. And they don't exactly have the same white puffy clouds that we see in the equatorial regions. Over time, Juno is going to allow us to build a detailed map of Jupiter's atmosphere. But for now, it's cool to just know there be water in them there clouds. Now, one of the complexities of trying to understand planet formation is things don't stay where you put them. Worlds that start in one orbit may end up somewhere entirely different as objects ranging from comets to ice giants to rocky asteroids all get tossed about through gravitational interactions. At more than 5 billion years old, our solar system has finally moved past the worst of the rock-flinging days. But there are still objects out there hitting our planet on a regular basis. Earlier this week, a meteor fell in Europe, and it seems that every month a new object is found passing between the Earth and the Moon. While we haven't found anything truly dangerous yet, it seems that at some point we are likely to find the next city or even civilization killer. Trying to figure out how to protect our planet is a top priority for a lot of scientists. And in a new paper in Acta Astronautica, a team of MIT researchers describe a new algorithm for deciding how different kinds of asteroids should be deflected based on their composition, orbit, and how far away they are when they are detected. It's a start. Unfortunately, we still have to develop the technology this algorithm counts on existing if we want to actually be able to take its advice and deflect asteroids. But that's a problem for another day. Luckily, we have nothing to deflect right now. For now, I'd like to round up today's episode by saying there's ice volcanoes in Michigan. Ice volcanoes have been detected in Saugatuck, Michigan, which is vaguely near Grand Rapids. These ice volcanoes on the beaches of Lake Michigan are being driven by water powering in through waves coming up under the ice that is built up on the shore, and it's getting released just like we think that cryovolcanoes may work on Lake Enceladus. So if you're in Michigan, first check the temperatures. These things will melt. And then go see if you can go see them. These are awesome. We will link to the article talking about where they are on dailyspace.org. Check back later today. But for now, that's all I've got. I will now stick around and take your questions if you're watching live on twitch.tv. And while you type them in, I'm just going to remind you, please use that purple circle with a purple star in the center. And while you type them in, I'm also going to remind you that this has been a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. I wrote today's episode. I am Dr. Pamela Gay, and this episode actually is going to get produced by me because Susie is off on a much-deserved adventure. Yeah, we are here thanks to you. Your donations through Patreon, and your subs and your bits right here on twitch.tv all go in to supporting us. If you'd like to see us grow, please consider giving. We're here strictly thanks to you. All right, that's it. I'm now going to look for your questions. I'm going to scroll all the way up to the top. Yes, I finally figured out how to reduce the volume on the rockets. I'm glad to hear I finally got them non-deafening. Took a little bit. Yeah, the open mic was an accident. That was a different problem. Sorry about that. I love your faith in my ability to meet things. It is a problem. It is a problem. All right. Let's see what else we have in here. Thank you, Keeper of Maps, for the bits. Oh, all the dogs heard me say thank you. Let me switch to a dog camera. Hi, I'm going to throw these. Go over there. Go over there. All of you go over there. Okay, fine. Only one of them understood they needed to go over there. All right, now you have fluffy butts that you can see. All right, so thank you. Let's see what else is in here. 51 Peg had a planet discovered in 1995. It's kind of amazing. Larry, baby stars to the tune of Baby Shark is just mean. It's just mean. So Hanny's Verb asks, wouldn't those worlds get blasted by nearby large stars at the end of their lives? Yes, and in fact, we believe that our own solar system was probably blasted by supernova early on in our existence. This is just the fate of planets. Luckily, they do tend to be far enough apart at the point that things start going supernova that the worlds are able to survive. It's just the life on them may not. It's a problem. Raj Luthra asks, do binary star systems take longer to form? No. From what we've been able to observe so far, binary systems, the individual stars in the binaries form the exact same way that singular stars form. It's just a messier situation because you have two interacting clouds of dust and gas. Scrolling to see what else is in here. Raj Luthra asks, is there metallic hydrogen in Jupiter? Yes, but it's much deeper down than what we're able to directly observe if our theories are all correct. But according to our pressure temperature models, yes, there should be metallic hydrogen deep down in Jupiter. There's a line going down the right-hand side of the image. I don't know which image. If you give me more information, I will try and fix it in the future. Oh, it's the corner of the green screen. Okay, that hopefully killed it. Sorry about that. I love everyone's like, field trip, let's go see the cryovolcanoes. I agree. If I still lived in Michigan, I would totally go see those. So Larry Weird, they don't specifically say nuclear bombs anywhere in this study. They talk about simply rocks getting moved by energy rockets. They don't say what kind of rockets. They allow that to be developed in the future. Looking to see what other questions we have in here. There's just a pile of emotes from Veronica Cure. I love your pile of emotes. Hanny asks, if we were on an asteroid, would we be able to lift large boulders unassisted? Oh yeah, we'd also be able to like jump off by accident. Yeah. The gravity on a lot of these asteroids is such that the force that our entire mass puts on the surface of the asteroid is the equivalent of the amount of force a piece of paper puts on your hand. And if you think of how little energy it takes to toss up a piece of paper, that's all the energy it would take to toss us, which is bad, because being able to jump off of rocks and end up lost in space is just bad. Only visit the biggest asteroids. Looking to see. A. McMullen asks, do other planets have ice volcanoes? We don't know if other planets do, but we know other worlds do. So Enceladus, Europa, Ceres. We don't know of enough water existing on any of the planets out there, at least in our solar system. It's a big, mighty universe filled with solar systems out there. Let's see what else we had. Dancing would be dangerous on asteroids. Do not dance on asteroids. Cannot recommend. Do not do. So I seem to have hit the bottom of the chat. I've still got to record today's episode and proofread the script and get everything posted. So Mythtown. If your asteroid's on a direct collision course, it is going to bring all the boys to the yard. All right. That's an image I did not need in my head. But you did it, Walker. Yes, that is true, Hanny. That is true. I'm just going to leave that one hanging out there. So many things are dangerous in space. Okay, Raj is asking a good question. Does dark matter contribute to the formation of the solar system? Not that we know of. Last estimate I read is in the entire volume of the Milky Way, there is the equivalent of 1 brick's worth of dark matter. So there's just not that much dark matter in our solar system. It's not going to have an effect. So thank you for the excellent question. Alrighty. So I will be coding this afternoon. I don't think I'm going to be streaming because I have a bunch of telecons I need to do. But I'll be hanging out in Discord. So hopefully I'll see some of you then. Tomorrow I will be back with the Daily Space. We also have Astronomy Cast running tomorrow afternoon. So many things going on. But for now, I am going to realize I forgot to turn my Stream Deck on, by which I mean I forgot to plug it in. Let's see what I can do to start credits rolling at a distance. I can do the thing. Your opinion on this equation. That it's a complete, so EG equals mgc squared is valid. I don't know what the SC to the 4th or the TC to the 5th are. So I'm fine with the first 2 parts of it. I have no clue what the rest of it is. Point me at a paper. I can give you a better set of words. But without knowing what all those variables are. Energy equals time C to the 5th doesn't seem right. So I just don't know what the T is. I also have no idea what the S is. So I'm going to give up from there and just say, yes, EG equals mgc squared is pointless, but valid. That's all I've got. That's all I've got. And the credits don't want to roll. There they go. Okay. I'll be on Discord. Ooh, there was a thing. I don't know what the thing was, but I'm going to thank it with bits. Do you guys want bits? Do you? Go over there. Go over there. Don't knock out the tripod. Oh, you're going to knock out the tripod. There you go, Eddie. This is how my camera ends up getting turned. So thank you guys. Let me figure out who I'm thanking. I'm on the wrong part of the chat. I don't know what I'm thanking. Yes, all three of them. So thank you all for being here. We will be back bringing you launches, landings, and anything scientifically interesting as it happens. And if nothing happens, we'll at least be back tomorrow at 10 a.m. Pacific, 1 p.m. Eastern, 6 p.m. London time to bring you the daily space. But for now, wherever you are in the world, have a fabulous morning, evening, or afternoon. And I'll see you on the other side. Bye-bye.